In the study of physics, mechanical work happens when you apply a steady force to an object and cause it to move. If that push stays perfectly steady, calculating the work is straightforward. You simply multiply the constant force by the total distance, or displacement. Work equals force times distance. This graph shows how constant force translates into a shape. When you plot a constant force on the y-axis and distance on the x-axis, the total work done is equal to the area of the rectangle they create. This clean geometry makes the math easy to visualize. But in the physical world, a perfectly constant force from start to finish is a rare occurrence. Real effort fluctuates. Muscles fatigue and mechanical resistance changes over distance. We call this a variable force, a push that changes as an object moves. When we graph a variable force, our clean horizontal line distorts. It warps into a jagged, unpredictable curve. The simple area formula no longer applies. We cannot multiply length by width because this new shape has no single constant height. To calculate the exact work done by a fluctuating force, we need a way to measure the precise area of this irregular shape. The solution involves breaking the complicated area down into microscopic, manageable pieces. We zoom in, isolating a tiny vertical slice of displacement called delta x. Within this microscopic window, the curve's variation is so minimal we can treat the top as flat, making the force temporarily constant. By isolating this sliver, we return to our original formula. We calculate work for just this slice by treating it as a standard rectangle. By treating a continuous, fluctuating curve as a series of isolated, frozen moments, we regain geometric control over the math. We zoom out, applying this logic to the whole path by filling the space under the curve with dozens of narrow rectangles. Adding these areas together gives a summation equation, providing a decent estimate of total work. But an estimate is not a measurement. Because the rectangles have fixed widths, their flat tops still leave tiny gaps and overhangs compared to the true curve. Calculus allows us to force the width of delta x toward 0. The rectangles multiply and narrow until they become infinitely thin vertical lines, perfectly matching the true curve. As slices become infinite, the summation morphs into the definite integral. Calculus provides the ultimate mathematical framework for measuring energy in a physical system where the input is never steady. We can see this math in strength on a coordinate plane. She begins pushing with 100 newtons of force, but she tires over the 20-meter distance until her force drops linearly to 50 newtons. To find the energy she spent, we calculate the area of the rectangle and the triangle under her specific sloping line. The total area comes to exactly 1,750 joules. Because this area resides above the horizontal axis, it represents positive work, the energy she injected into moving the trunk forward. But the platform is rough, which generates a constant 50-newton frictional force fighting against her push. Because friction opposes the motion and takes energy away from the system, it is graphed of a negative value. A flat line appears below the axis at negative 50 newtons. We calculate the area of this lower rectangle to find the negative work performed. Negative 50 newtons over 20 meters equals exactly negative 1,000 joules. To find the net work done on the trunk, we combine these two areas. We take her positive effort of 1,750 joules and subtract the 1,000 joules lost to friction. The definite integral accounts for every joule of energy added to the system and every joule the environment takes back, totaling the net work performed.